So welcome all. In this class, we are going to discuss some mysterious results in quantum mechanics. And we will do that by performing a thought experiment. This experiment is very similar to Young's double slit experiment. That is a very popular experiment in optics in which we observe interference of visible light. But here, in place of that visible light source, we are just using an electron gun, which may be say a cathode ray tube capable of emitting cathode rays with an angular distribution. Now, you must be familiar with de Broglie's hypothesis, which states that the motion of quantum particles like electrons may be described as a wave of wavelength lambda given by h by p, where h is the Planck's constant and p is the linear momentum of the electrons. Now, these cathode rays proceed towards this wall, which is capable of absorbing all the electrons except those that pass through the holes 1 and 2. Secondary wavefronts are generated at the holes, and these wavefronts proceed towards the screen where they interfere, and they interfere with a definite phase relation that is dependent on the x position. We take the x direction along the vertical as shown here in this reference frame. The intensity can also be detected by a detector which is capable of moving along the x direction, and if we plot the data, we will observe an intensity distribution like this. This is called an interference pattern. You can observe that there are several points where the intensity is very high. At these positions, the two waves meet in phase where there is constructive interference, and there are also several points where the intensity is very low. At these points, the waves meet out of phase and there is a destructive interference. So this is a very standard result in optics. Now, next, if we close one of the holes, say we are closing hole 2, then the electrons can pass through hole 1. In this case, there is only one set of wavefronts that fall on the screen, and there is no question of interference and no question of a definite phase relationship. So simply we will observe this kind of standard intensity distribution given by curve P1, and conversely for the hole 2 we will observe curve P2. Now you can see that this intensity distribution, the interference pattern that we observed in the previous case, is not given by the sum of these two simple intensity distributions. That is because of this interference occurring in this in the previous case, and this behavior is can be explained by this equation, where the third term basically accounts for the interference, and the angle delta is the phase difference between the two waves appearing meeting at a certain x point on the screen. So now the interesting part of the experiment comes. Now we want to observe the electrons and locate through which hole a certain electron is passing. For this, hypothetically, we can employ a very bright source of light in between the holes 1 and 2. So that light source will emit a large number of photons, and the electrons, while passing through a certain hole, will be scattered by a photon, and there will be hypothetically say a bright flash when we can observe that, and also after being scattered, the electron will lodge at a certain x point on the screen and it will be detected by the detector. Now, interestingly, immediately what happens is that this interference pattern is destroyed, and we observe a curve like this one, which is simply the sum of these previous two curves P1 and P2. We would have observed the same curve if we would have done this experiment with macroscopic objects, like say if we would have scattered bullets in using a machine gun in place of this electron gun. So this is a very simple explanation, just the sum of the individual intensity distributions. So what happens is that when an electron gets scattered by the photon, and since the energy of the photon and the electron are of the same order, this photon imparts some amount of energy to the electron, and the electron gets scattered and deviated from its path, and randomness occurs. The phase relationship is lost, and the electron lodges at a certain x position just randomly, and a simple statistical distribution will explain this curve. Now, next, if we want to restore this interference pattern, then there may be two ways. First, we are going to reduce the intensity of this light source. So in that case, what happens when the intensity is quite low? Then basically, intensity means the number of photons being emitted from the light source per second. In that case, when the intensity is quite low, some of the electrons may sneak past our observation, and we are basically not capable of observing those electrons, and some of the electrons will scatter the photon and the flash will be observed. but we can very well locate the electron through which hole it is passing. Now in this case there may be three kinds of electrons. The first case, we have located the electron that it passes through hole 1 and observed it. We have located the electron that it passes through hole 2 and observed it. And in the third case, the electrons, those that we have not observed. So the first two sets of electron will simply give this curve p12 prime, because those electrons get scattered by the photon, and the third set of electrons will simply produce this interference pattern. And this is also explainable because situation is very similar to the first part of the experiment where we have successfully constructed the interference pattern. Now the second method may be by reducing the frequency of the light. That means we want to reduce the energy, or equivalently speaking, we want to increase the wavelength. So initially nothing happens, but at a certain point, when the wavelength of the light becomes comparable to the distance between the two sources, at that point we just start to observe the interference pattern. There is some interference, but interestingly, since the resolving power of light is of the order of the wavelength of the light, and here the wavelength is of the order of the distance between the two source slits, in that case the flash of the light will be very much diffused and we will be unable to locate through which hole the electron has passed. That means we will not be able to locate the flash of the light, either it is close to hole 1 or close to hole 2. In this situation, the interference pattern begins to be observed, and if we increase the wavelength further, the intensity pattern, the interference pattern will be restored, but we will not be in any place to locate through which hole the electron has passed. So our conclusions are that, number one, if we are able to locate the electron, then the intensity interference pattern is destroyed. Number two, if we have restored the interference pattern, then we are completely unable to locate the electron through which hole it has passed. So this is basically Heisenberg's uncertainty principle, and I leave it a task for the students to study Heisenberg's uncertainty principle and provide an explanation for it in the general case. Thank you.